don't feel shy. I mean, these concepts are not very well known, and they are not in books either. You will not find a book that tells you that your quasi-steady lift is your aerodynamic input. These things are not that mature to the level that it become, it's shown, it's found in many books. No, I'm not aware of a single book that tells you that your quasi-steady lift is your aerodynamic input. I'm just trying to encourage you to ask questions. These things are not very mature, so it's very fair that you do not grasp it very well. Please come up with questions so that we can discuss. Okay, so luckily this C of k has an analytical expression. It's a fraction. It's h1 2 of k divided by h1 2 of k plus I h0 2 of k. So these are Hankel functions, and luckily we have MATLAB functions for them. So the numerator, for example, is simply Bessel h of, you give it the order 1, you give it the kind 2, and you give it the argument k. Okay? So you can compute at any k, give me any k, I'll give you C just by this line in MATLAB. And as you can imagine, it's complex number, because you have I here, I there. So whatever comes out of this thing, and even in the computation thing, we have I downstairs here. So C of k is a complex number for a given k. Okay?
Sir, I have a question.
Yes,
How do we find out the parameters which we need to put in that function?
The parameters between?
Which we need to put in that like MATLAB function. Like how do we compute those parameters?
Which 1 and 2 or k or what?
Like 1 or 2.
No, this is, to do some function is done now. This is, so this is equal to or equivalent to, or its definition, whatever. This will be always 1 and 2, 1 and 2, 0 and 2. These are functions.
Okay.
So
how do we do
h1, 2 is a specific function. It's a Hankel function of order 1, second kind. So it will always be like this. The only variable in the right-hand side, as well as in the left-hand side, is k.
Okay.
You give me your frequency,
Right.
and the dimensions and thing, I get my k, use non-dimensional frequency. I should plug it here, I get a complex number. Okay? So, let's talk a little bit about C of k. So, if it's a function of frequency, here is how it looks like. This is k. Please keep in the back of your head that k is omega. Okay, it's frequency, but non-dimensional thing. And the same here, k. It's a complex number, so it has magnitude and phase. Angle, okay? Tan inverse imaginary over real. This is square root real square plus imaginary square. At k equals 0, this is unity. And it's doing like this. Its asymptote at infinite k is half. And this guy, at k equals 0, it's 0. It attains a maximum about negative 15 degrees, so not so much, at around 0.3 k, and comes back to 0 again. Okay? So let's look at that. So my total lift as a function of time. Again, what's my problem? I have a moving airfoil moving around, and I want to get, I know the motion as a function of time, my input as a function of time. I want the lift as a function of time. This is my output. We said this is 2 parts. The non-circulatory part is very easy to get. It's negative pi rho b squared, your normal acceleration at the half-chord point. So the first part is very easy. Plus, the second part is whatever steady lift you're expected. What's the steady lift I'm expecting? Well, it's y, right? It's 1/2, I'm sorry, it's not pi. It's a rho u squared b, right? This is times your left coefficient. 1/2 rho u squared c, my chord is 2b, right? So rho u squared b times my CL. My CL steady is 2 pi alpha 3/4, right? This is your quasi-steady lift as a function of time, your input. Okay? Times, here is the equation. This guy is the quasi-steady lift times this huge integral which reduces down to C of k. Okay? Any question about this equation? So this is your total lift, we're done. We'll see how to apply it, but let me know if you have any question now. Any question, please?
I want to ask a question.
Sure.
So we are talking about the total lift. I mean, why is it called total lift? Is there a non-total lift?
No, I'm saying that now we're adding the non-circulatory, remember the old component, plus the circulatory. But if we are in a paper or something, we don't use total. It's just, this is for illustration for us.
So it's just circulatory plus uncirculatory?
Yeah.
Oh, I see.
The entire lift force that we have.
Ah, okay.
Okay? This is the essence of it, because this guy is the lift that we really know. This is something new that we learned in unsteady flow, right? And we said that it's more of a resistance than a lifting force. But anyway, let's see here. Give me the airfoil motion as a function of time, please. I immediately get the acceleration. That's very easy. And this is really a function of time. That's fine. Here we have the angle of attack at 3/4 as a function of time. That's okay. But now, what is this? This is a complex number, right? It depends on the frequency, but at the end of the day, it's a complex number. So how can I multiply this? How can I do this multiplication? This is the point, okay? So we interpret this as a frequency response kind of thing. So when you have here a system, this is G of, what do you call the Laplace thing? S?
S, yes.
Yeah. Unfortunately, the unsteady aerodynamic people, they use the S for something else. So I'll use P, because they are not dynamics and control people. Anyway, so this is G, let's say it's P. This is your input, and this is my output. The way we interpret the frequency response, do you remember how to get the frequency response from a transfer function? How to get the booty from transfer function? What's the very first step? Replace each S or each P with
J omega.
J omega, exactly. Let's say I omega. So your frequency response to Dawson function is actually the transfer function of the flow replacing each Laplace with I omega, okay? Non-dimensionally ik. So if I have an input that is A cosine omega t, what's the output here? Well, it's A cosine, the same frequency, but I have two different things. The amplitude is magnified by your transfer function. Okay? So this guy, it's a transfer function of P or S. Place each P with I omega, so you get a complex thing, depending on omega. The magnitude of which, it magnifies your magnitude, and the phase of which, it modifies your phase, G of I omega. So it's the exactly same thing here, the exactly same concept here. Deal with C of k as C of k for us is exactly the frequency response, in the sense that it's our transfer function after replacing each P with ik. Okay? So the magnitude of which will be multiplied by the magnitude, and the phase of which will be just modifying the phase. From this point of view, our aerodynamic input is what? What's our aerodynamic input? What is our aerodynamic input? So for us, this is C of k. Here is, whatever you want to call it, let's say that this is your steady lift or quasi-steady lift. Okay? And here is the circulatory lift. I'm not talking about the other part because the other part doesn't have dynamics. Give me your time, give me your airfoil motion at this time, I give you the lift at this time. But this guy has dynamics. So if you look here, this means that at zero frequency, this is the magnitude which will multiply your lift magnitude, right? Remember, this magnitude will multiply the magnitude of the input. What is my input is the steady lift, okay? So whatever value here will be multiplied the magnitude of the steady lift. So at zero frequency, it's 1. Makes sense, right? At zero frequency, I'm steady, so I'm multiplying by 1. But this means what? This means that any unsteady lift, any unsteady circulatory lift is less than its steady counterpart, right? Because everything is lesser than 1, at least in the small angle of attack regime. So your unsteady circulatory lift is always less than its steady counterpart. This is a problem. Why? Because if you're designing something to operate unsteadily and you're expecting some lift variation, some lift amplitude, you will not get that. In reality, you will get less than that. Okay? So this is important to take into account. And the phase here is the amount of lag that you get. And it says that it's not that much because the maximum phase is negative 15 degrees. It's not that much. We'll talk about it later. But this is Theodorsson in a nutshell. Let's try to apply it in special cases. So let's here consider a special case of a plunging airfoil. Talk about plunging, pitching. Any question, please? Do you have any question? Come up with it.
Yes, I was wondering, what if with the unsteady, the unsteady circulatory is not at the same direction with the steady oscillator?
The unsteady circulatory, this guy, is what? Is
sorry.
Okay. So plunging, I have an airfoil here that is just going up and down with h of t positive downward, the same as Theodorsson, is maybe large h sine omega t. Okay. I immediately can get the velocity and the acceleration, right? So this is h omega cosine. This is negative h omega squared sine, right? What do I need? Well, I have two kind of inputs. For the non-circulatory lift, I need the acceleration, and for the circulatory lift, I need the angle of attack. Okay? So the acceleration, the normal acceleration at any point, because this is uniform motion, so the normal acceleration at any point is the same. In particular, the normal acceleration here at the half point is simply negative h double dot. Okay? So this is negative h double dot, so it's h omega squared sine omega t. So this immediately tells you the lift, the first part of the lift. So the lift as a function of time is negative pi rho b squared, your added mass, times the acceleration. Here is the acceleration, h omega squared sine omega t. So always the first part is easy. Give me the acceleration, give you the lift at this particular instant. There's no dynamics. In reality, there are problems which Amir has found in his simulations, and we can talk about these advanced stuff towards the end of the course. But this is the theory. Okay, now plus, the other thing is, just give me my actual aerodynamic input, which is the angle of attack at the 3/4. Again, because it's uniform motion, all the points see the same angle of attack. Doesn't matter from a point to another, they all enjoy the same angle of attack, which is alpha at any x actually is negative, h dot divided by u, right? Approximately, because it's supposed to be 10 inverse. But it's a small angle. So this is h dot divided by u, so omega over u, can multiply and divide by b, so I have k here, cosine omega t. You don't need to multiply and divide it, it's just for convenience. And the h hat is the normalized thing, So h hat is the normalized amplitude. H divided by semicolon. Okay. You don't need to. You can just copy the h dot and divide it by u. So this is your aerodynamic input. Please pay attention here. Please, please. So my aerodynamic input, I'll put it here. Let's see how we construct it. How you construct the steady lift out of that? Well, it's rho u squared b times the lift coefficient, which is 2 pi alpha. Here is alpha, right? Okay, so this is now the steady lift. To get the unsteady out of it, I need to simply multiply by c of k. So I need to get k first. Well, k is easy. K is, tell me your frequency, I will get my k. So I got my k. Then go and substitute here to get c of k. C of k is a complex number. The magnitude will be multiplied, and the phase will be added here. Okay? Did you get how to construct the unsteady lift? So construct the steady, but it has to be cosine and sine. It has to be cosine and sine. So that I can modify the amplitude of the harmonic motion, cosine and sine, and modify the phase. Let's get another example for a pitching. Pitching airfoil. If you have a question, stop me, please. The midterm is next Wednesday, right? It's take home, and it will include Tidurson, it will include computation of unsteady lift due to Tidurson. So if you have a question, please stop me. It will be after this lecture. Next lecture will not be included, of course. Another example, pitching. So this is my airfoil. Maybe this is half. It's not quite half, but I need to zoom. This here's the hinge. So this is AB, if you remember. We like the 3/4 chord. So this is actually, this is B over 2, right? We have alpha here. We're rotating about this hinge. It's A sine omega t or cosine, doesn't matter. So I can get my alpha dot and alpha double dot I need it for the acceleration. Omega squared. So get the velocity at any point x here, maybe, any point x. Any point x. Give me the velocity, the normal velocity at any point x is, remember this is moving with u, and this is alpha. So u cosine gives you tangential, u sine gives you normal, and we, for Tudorson kind of thing, yes, Anshul?
In this case, what is the difference between omega and alpha dot?
Omega is equal to alpha dot. Omega, no, I'm sorry. You're saying this omega?
Yeah.
This omega is the frequency.
Frequency.
It's not the angular speed. I thought you were asking. The angular speed is the same as alpha dot. That's right. But this is the frequency, how fast you're moving.
Oh.
Okay?
For the frequency of plunging.
Here we're doing plunging, how fast you're moving. Okay? Here we're doing pitching.